Hello, my name is Manuel Garcia, and today I'm with Team 5 Personas to present our semester-long project with the company APTIV. This study was to learn more about drivers' experience with partial automation. Firstly, our objective was originally to understand how drivers' needs, intentions, and experience vary across highway and urban environments with partial automation. However, our scope changed throughout the processes of our study. It later formed into how new drivers build trust with the Tesla vehicle with the system's user interface. These objectives were changed once it was determined that on-road testing was no longer viable for this study, which will be explained further in the presentation. For our product, we utilized Tesla's autopilot system and in-vehicle interface in conjunction with experienced and first-time Tesla users. Our methods for this study range between interaction maps, sit-down interviews, affinity wall, a comparative evaluation, a heuristic evaluation, and finally, usability testing. Our goals for this study was to understand the differences in driving experiences between highway and non-highway environments, as well as how autopilot features are integrated into drivers' everyday commutes, and to what extent do drivers trust the existing autopilot features while driving. Here's Chris with our study's personas.
We created 3 user personas to represent varying degree of user trust in autopilot systems. The most representative user persona is Alina. She is an experienced Tesla driver who is unprepared for troubleshooting autopilot features in high-tension driving scenarios. She also feels lack of trust in the system, especially in non-highway settings. And her goal is to intuitively utilize features with full knowledge on how to respond to alert systems and also build trust with autopilot system through practical use on both highway and non-highway settings.
Hi, this is Orville. Before we jump into our findings and recommendations, I just want to explain that our project was broken down into 2 distinctive phases. The first where we were looking at driver behavior, intentions, motivations, and the second phase looks at the Tesla HMI of Model 3 specifically and the usability surrounding that. So, jumping into our findings and recommendations from phase 1, we found that drivers will only use autopilot features when it's helpful. How can autopilot not be helpful? It literally takes the driving out of driving. Well, when the system breaks or fails, such as in ghost braking where the car suddenly brakes for no reason, the drivers lose trust in the system, and as a result, they think that the system can only handle very low complexity environments, and they experience an added attention cost of now having to constantly monitoring the environment for any changes in the environment, any changes in complexity. And that kind of creates a vicious cycle of once you lose trust, there will be very little chances to reestablish that trust because drivers are most likely going to not use the system going forward. To resolve this issue, we took a 2-pronged approach, which is to remove the need or the cause for the added attention cost, and 2, to just break less trust in general. How do we do that? Well, provide drivers with feedback when the complexity environment increases, as well as when the vehicle's certainty in its evaluation of an environment drops below a certain threshold. This way, the drivers no longer have to be on the lookout because the car will be on the lookout for the driver, right? And 2, to focus on ghost braking and other failures that are mainly founded in low complexity environments, which we can think about as the places where drivers are most likely going to be first testing their new system, what it can handle, what it can't handle. And so by fixing the errors found here, there's going to be less trust broken in general and from the outset. Now, jumping into phase 2 of our project, looking at the HMI of Tesla specifically, we found that in our usability issues uncovered, we were able to extract overarching themes in those issues. The first one being a significant inconsistency of elements with the standards set by the industry as well as by the system itself. The car icon does not look like a menu system icon, right? The checking tire pressures and adjusting mirrors can't be done by interacting with the mini 3D model that you would use for opening the doors, the trunk, the frunk. Checking the battery status as distance is impossible through the menu system. You actually only have the shortcut, which is a tiny little number at the top and you have to click on the battery percentage number. So there's a lot of inconsistency in how Tesla handles interactions, how you do things, how things are displayed in general. Our recommendation for this is to establish a consistent design language and interaction language. Elements only significantly deviate from industry standards in meaningful and intentional manners, and when deviating improves the understandability of the element. And deviations should only occur in isolated incidents and communicate as deviations. This includes fixing the car icon, building in the shortcuts for mirrors and tire pressure, and as well as building in the functionality of checking battery status in the menu system.
Another overarching usability issue we found is that affordance are not properly communicated to be present, which means it has no signifier or signifiers do not sufficiently communicate the feed forward. For example, we found that a lot of interactive components or icons in Tesla's user interface do not communicate as the buttons, such as the car icons on the bottom left of the screen to bring up the control hub, where most adjustments are made. The battery range and battery icon are two different buttons, but communicate as a single element that is not interactive. Climate control adjustment displays as a non-interactive task component when the screen brightness is not optimal. Most failures in tasks are highly associated with the components listed above, as users didn't perceive them as intuitive and interactable components. As a result, we recommend, when designing a user interface, ensuring that signifier of interactability and feed-forward are sufficiently present, discoverable, and understandable for all interactive components within the system. This ensures users know what they can interact with and what that interaction will result in.
While we benchmarked with Tesla to study drivers' intention and behavior using autopilot features, we would like to discuss the pros and cons of this approach in the last part of our presentation. Since Tesla is one of the well-adopted products in the market, we got to have the chance to study its system and user experience from a big user pool. Nevertheless, we also question that the insight we found might not be able to transfer into our clients' future design for their own assistant driving feature. For example, the usability issue we found from Tesla's models might only be Tesla's design flaw, and our client might not have this sort of design at all. And in this discussion, we would also like to highlight the restriction of performing on-road testing. While there is a safety concern from the school that stopped us from executing the on-road interview, we missed the chance to observe and dive deeper into driving intention of interacting with assistant driving features. This approach is particularly important for this project, for us to study driving behavior from creating certain environments such as highway and urban roads. And due to this restriction, we shift our research plan for usability tests from an on-road testing with Tesla's autopilot features to an onboarding experience evaluation with new user interacting with a stationary car.